So bonjour, hello everyone. I have only 15 minutes, so I've got a lot to get through, so I'll quickly talk through it. So we have a short-term response to hypoxia. We have a stress response. I'll talk a bit about hypoxia-inducible factor, HIF1 alpha, later on, and we have increased production and release of many mediators, nitric oxide, reactive oxygen species. And many changes occur: cardiorespiratory, cardiac output, vasodilation, mechanical ventilation. There's a redistribution of organ flow, a reprioritization of cell work, and changes in bioenergetics and metabolics. Okay, we published this a couple of years ago, where in a rat model we either did hemorrhage, hemodilution, hypoxemia to get a 50% reduction in oxygen delivery. Obviously in the saturation, the hypoxemia dropped, the lactate went up equally, the urine output was a bit different between the groups. Next please, thank you. You can see this is in the sham animal, the hemodynamics. Next please. So with hemorrhage, sorry, it doesn't show very well, there was, not surprisingly, a fall in the flows and the oxygen tension. With the hemodilution, again, similar changes. Next slide. However, with hypoxemia, you had a larger fall in the tissue oxygen, but a recovery in the renal blood flow, a preservation of the aortic blood flow. So very different changes. Thank you. And hormonally, the changes in norepinephrine, corticosterone, rats don't produce cortisol, vasopressin were very, very different, although the rise in glucose was the same as a stress response. So you'll hear later on from Jean-Charles about that. So the body responds differently. The same reduction in oxygen delivery, but very different responses. Please. So metabolic demand is matched by the generation of ATP. So when we exercise, we increase demand, and when we sleep, we reduce demand. Most of the ATP in most cells of the body is aerobic, from mitochondrial oxidative phosphorylation. A small amount, so apart from red cells, a small amount comes from anaerobic metabolism, glycolysis. This is a mitochondrion. Next, please. So glycolysis, glucose to pyruvate. For every mole of glucose, you get 2 moles of ATP. Next, please. You get, from the Krebs cycle, a further 2 moles, and that's where the carbon dioxide comes from. Back a bit, thank you. And from the electron transport chain, you get 26 to 30. So the aerobic, because the oxygen is used here, complex 4 of the mitochondria, that's where most of the ATP comes from. Thank you. Next slide, please. So ATP generation is mainly aerobic, but it depends on adequate delivery of oxygen and substrate to the cells. So we have the heart, the lungs, the circulation, the hemoglobin, carrying it through the microvasculature, through to the cells, through to the mitochondria. This is a really nice, very big review of oxygen utilization. So this is how much oxygen we consume, the majority being by the mitochondria. Of that, you have coupled and uncoupled. So most of the oxygen's coupled to making ATP. A proportion is lost, but is important for heat generation, etc., but also it can protect against free radical damage. Next, please. And the aerobic ATP production goes towards a whole load of synthetic and pump activities, membrane maintenance, etc. So this is in the liver, for example, but protein, sodium pumps, calcium pumps, gluconeogenesis, etc. Repair. All of these are energy dependent, ATP dependent. Next, please. Next. And next. Okay, so you have a gradient of oxygen tension from the artery right down to the mitochondria. So if you've got 100 millimeters in the artery, it's somewhere around 1 to 10 at the level of the mitochondria. Next, please. What happens, and again, please, you have convective flow. Next, please, thank you. Where you carry through the oxygen delivery components to the arterioles, and then that's convective flow, and then you get diffusive flow, not just from the capillaries, but from the arterioles and the venules through the tissues into the mitochondria. You also can get AV shunting, which is... Oh, sorry, we're going a bit too quick. Okay, and forward, please. You also get AV shunting, so you can go straight from arteriole to venule, bypassing this whole network. Next, please. So it all depends on the mitochondria, how much oxygen they need. So if that goes up, there's an increase in metabolic demand, an increase in need. The oxygen tension in the mitochondria will drop if nothing else changes. Next. And that signals back to the cardiac output, to the local blood vessels to increase cardiac output and dilate. Next, please. So the idea is you give more oxygen to these more metabolically demanding cells and you restore the oxygen tension. So the vasculature senses the amount of oxygen at the level of the mitochondria and the tissue. Next, please. On the other hand, if mitochondrial utilization drops, that has a negative feedback, so you don't need the oxygen. Oxygen is toxic, so the body, the cell, the mitochondria wants to regulate how much oxygen it's getting, and so, next please, that constricts, and as a result you get a reduction in the amount of oxygen being delivered because the cells say, leave me alone, I don't want any more. Next, please. Mary Ellsworth is in Canada, and some very elegant work she's done where she's suggested that the red blood cells actually can also sense the oxygen and then modulate vascular tone. So if the cells have a high oxygen demand, so metabolism's exceeding delivery, or there's hypoxia, so that the metabolism isn't being met by an adequate oxygen delivery, you have a fall in the local hemoglobin saturation. And that causes the red cells to release ATP, which then works on purinergic receptors on the endothelium to trigger vasodilation. So she's suggesting hypoxia locally and a drop in hemoglobin saturation triggers the red cells to modulate vasodilation. Next, please. We're brought up thinking about oxygen delivery being, oxygen utilization rather, being delivery dependent. However, next please, perhaps we should think about it more in terms of a vacuum cleaner. The cells want more oxygen, they pull. So keep going. Press, 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 press. Thank you. So think about it more as... thank you. Think about it more as the cells perhaps wanting, pulling, sucking the oxygen rather than the standard delivery. Next, please. Oh, no, forward. Thank you. Okay, so when we have the oxygen delivery equation, we have three components of hypoxia. Anemic, when the hemoglobin's low, circulatory, and hypoxic, when the saturation's low. Next, please. And when you have a problem at the cell level, the oxygen's there but not being used. So like sepsis, for example, that seems to be the case when the mitochondria are poisoned. Dysoxia. Next, please. So, oxygen's delivered to keep the ATP level stable. If the oxygen delivery drops, if metabolism continues at the same rate, the ATP level will drop. And that will trigger cell death pathways. So at a certain threshold of ATP, you'll get cell death. Very quickly, the cell tries to compensate. You get dilatation to try and improve the blood flow, improve the oxygen delivery, and you get an increased reliance on glycolysis to try and support, not as efficiently, but try and support ATP supply. And that will hopefully normalize the ATP level or only drop it a little bit, but not enough to trigger cell death. And that hopefully will allow the cell to survive. But in the longer term, if the delivery is not restored, if you shut down metabolism, you can then rebalance supply and demand. Next, please. But it means that the cell is surviving, but it's not functional. So it's basically switching off, hibernating as a strategy for long-term survival. Thank you. This is written by a zoologist at Cambridge University. He looked at cell survival in hypoxia, hypothermia. The key to survival lies in an ability to downregulate metabolism to a new hypometabolic steady state, such that ATP demand and supply is rebalanced. Next, please. And again, and again. So it depends how aggressively this happens, but you get this turnover of ATP, either when it's forced or when it's regulated. Next, please. Just to give an example of the kidney. So this is work done by Bob Schlichtig years ago, a dog model. They hemorrhaged the animal, and at a certain point there was the dependency between delivery and consumption, whole body fell. So the consumption was maintained until the delivery fell quite significantly before that fell. Next, please. On the other hand, in the kidney, you didn't get this relationship, this biphasic relationship. It was linear from the beginning. So as the kidney oxygen delivery dropped, the consumption dropped. This is work we did. This is a hemorrhage model. So we just progressively hemorrhaged these rats. Blood flow, aortic, renal, dropped. They became more acidotic. And we measured the oxygen tension in the muscle, bladder, liver, kidney. And again, the muscle, the bladder, the liver all dropped. Next, please. But if you look here at the kidney, it stayed remarkably normal until the very end, until the animal was pre-terminal. So despite the renal blood flow plummeting by more than half, the PO2 in the kidney was maintained. What does the kidney mainly need energy for? It's to resorb most of the fluid and salt that's filtered out with glomerular filtration. Next, please. So again, there are different mechanisms that cause it, but nitric oxide has been implicated. Nitric oxide's released very quickly with any stress, hypoxia, tissue hypoxia. And this is a nice study from the Hintzer group where they blocked nitric oxide synthase. And they found that the GFR in these animals halved. Sodium reabsorption halved as they went up and up on the dose. But the oxygen consumption doubled. So interestingly, it looks like nitric oxide seems to regulate, control renal oxygen consumption. So it's a way, acute illness of perhaps reducing GFR and reducing the workload of the kidney, at the same time trying to effectively, efficiently keep resorbing sodium. Next, please. A few quick words on HIF. I've got about a minute to go. HIF is a sort of master regulator. Slide, please. Yep. So it works, it activates different receptors. So the glucose transporter, please. Glycolysis is upregulated again. It inhibits, though, PDK1, so pyruvate going into the mitochondria, so it downregulates oxygen consumption. But it activates lactate dehydrogenase to recycle NAD+ to be used in glycolysis. Next, please. And this nice study here showed in hypoxia, these are cells, next please, that the rate of fall of oxygen in a closed cylinder, so that's a marker of oxygen consumption, was considerably reduced in hypoxia. I'll go to my conclusion. There are very many different ways of responding to any hypoxic insult, short-term and long-term. And it, again, very organ-dependent. I was going to show you similar effects in the kidney to the heart and the brain. So these organs have the ability to switch off. You'll have heard of myocardial hibernation. that's a similar way. So when the heart remains ischemic, or bits of the heart remain ischemic, the contractility goes down to reduce the metabolic demand, and when things improve, it works again. So the body's a really, really clever organism. Apologies for all the AV issues. I hope you've been able to follow me. Thank you for listening.